Today we will look at the solution of the Bessel's equation. Bessel equation, as we have seen earlier, it is x square d square y by dx square plus x dy by dx plus x square minus n square y equal to 0. So this is the Bessel's equation, and we are going to find solution of this Bessel's equation by using the Frobenius method. In last class we have obtained solution of SHO, simple harmonic oscillator differential equation, using Frobenius method. By following the same procedure, we are trying to obtain a solution. We know the Bessel equation has a regular singularity at x equal to 0. Okay, x equal to 0 is a regular singular point, and there will be at least one solution. We are expanding about x equal to 0, and we can get at least one solution that we will see. So we know the solution that we assume is y equal to sigma lambda 0 lambda a lambda x minus x0 k plus lambda, where x0 is the point of expansion and we are taking x0 as 0. So we have y equal to sigma lambda a lambda x to the power k plus lambda. So this is our y. x0 is 0. Okay. So dy by dx will be this. We differentiate this. So we have a lambda k plus lambda x to the power k plus lambda minus 1, and d square y by dx square, that will be that is given by, when we again differentiate this, we will get this a lambda k plus lambda minus 1, and the power of x now becomes k plus lambda minus 2. Okay, so this is d square y by dx square. So this is y, this is dy by dx, and this is d square y by dx square. This we substitute in this equation. We substitute here for d square y by dx square, we substitute for dy by dx, we substitute for y, we substitute. So as we substitute, we will be getting this. Okay, as we substitute, we will get this. Okay, and for x square minus n square, we will have two terms. Like this, we will have two terms, and altogether we will have 4 terms. Okay. So as we substitute in our Bessel equation, we will be obtaining this. Now, as we did earlier, we equate the coefficient of lowest power of x. Okay, we equate the lowest coefficient of lowest power of x to 0, because on the right hand side it is 0. Lowest power of x is obtained when we put lambda equal to 0. So we have x to the power k here. Here also x to the power k. Here you will have, when you put lambda equal to 0, you have x to the power k plus 2. Okay, so that we are not taking here x to the power k. So we will have coefficients from these 3 terms. Okay, where x to the power k. So the coefficient of x to the power k, that is a0 k into k minus 1, a0 k minus n square a0 equal to 0. And from this one can write this as a0 like this, a0 k square minus n square equal to 0. And we know a0 is not equal to 0. If a0 is not equal to 0, what will happen? This has to be 0. K square minus n square has to be 0. So k square is equal to n square, k equal to plus or minus n. So the integral equation is k square minus n square equal to 0, and we have k equal to plus n and minus n. These are the roots of this integral equation. So when we equate the coefficient of the lowest power of x, we will get k equal to the integral equation, which is k square minus n square equal to 0, and the roots as k equal to plus n and minus n. And then what we do, we equate the coefficient of the next lowest power of x, which is x to the power k plus 1. Okay, so that we obtain by putting lambda equal to 1. Okay, so we will have x to the power k plus 1 here. Here also k plus 1. Here you will be having k plus 3. Okay, so we need not take this. Here also, here you will have x to the power k plus 1. So we have to take these three terms. Okay, so the coefficient as we take, that is given by this a1 like this, and you can write it like this: a1 k plus 1 square minus n square equal to 0. Okay, so this is this can be written like this: k plus 1 plus n into k plus 1 minus n. And when k is plus n, when k is plus n, this k is plus n, you will have a1 into 2n plus 1 equal to 0. Okay, and if n is an integer, a1 has to be 0. If n is an integer, this has to be 0. If n is say some minus half, then this will be 0, n is minus half, but a1 will be arbitrary, and we are choosing a1 as 0. Okay, and when k equal to minus n, this will be the case, and we will have a1 minus 2n plus 1 equal to 0, and you know, for n integer you have a1 equal to 0. So a1 is 0. Okay, so this is what we obtain from the second step: a1 is equal to 0. Then the coefficient of x to the power k plus j, coefficient of x to the power k plus j we are taking. So how do we get the coefficient of x to the power k plus j? What we do is, here in the general equation, here you put lambda equal to j. Okay, here also you put lambda equal to j. Here you put lambda plus 2 equal to j. Okay, here you put lambda equal to j. So the first term you put lambda equal to j, the second one lambda equal to j, then the third one lambda plus 2 equal to j, and we get this equation. We will be obtaining this. Okay, and we will have an expression for aj. Okay, aj into k plus j square minus n square plus aj minus 2 equal to 0, and we have aj equal to minus of aj minus 2 by k plus j square minus n square. So this is the recurrence relation. So this is the recurrence relation. So we have obtained the recurrence relation. And here now we have to take the two roots. When k is n, we put k equal to n here. So the recurrence relation becomes this: k equal to n, and you have this aj equal to minus of aj minus 2 by j 2n plus j, and then when we put j equal to j plus 2, here you put j equal to j plus 2 here also. So what you get is this: aj plus 2 equal to minus aj by j plus 2 into 1. So this is what we get. And if a1 equal to 0, okay, a1 0, then a3, a5, all of them are equal to 0. We know a1 is 0. We have seen in the second step that a1 is 0. So if a1 is 0, a3 will be 0. Okay. So a5 will be 0. So we will get a1, a3, a5, all of them as equal to 0. The odd coefficients as equal to, or odd values of a, that will be equal to 0. And for even values, we have, for a2, we will be getting this. a2, we are trying to find a2. We put j equal to 0, so we have minus a0, this minus a0 by 2 square, 1 factorial n plus 1, and we introduce a n factorial by n factorial. Okay, here. So in the numerator, we will have minus a0 n factorial. Here you will have n plus 1 factorial, because the n plus 1 factorial and n plus 1 into n factorial will combine, and we will have n plus 1 factorial here. Okay, so this is a2 and this is a4. When we put j equal to 2, we can get a4, and a2 we substitute from here, and we will get this. Okay, a0 n factorial by 2 raised to 4 by 2 factorial n plus 2 factorial, and this will be a6. Okay, and we can write the general relation a2p equal to minus 1 to the power p a0 n factorial by 2 to the power p factorial n plus p factorial. Okay, so we have got the recurrence relation. We know all the odd values are 0. We can obtain even values a2, a4, a6 from this. Okay, so our general relation, the solution that we assumed is this: y equal to sigma lambda a lambda x to the power k plus n. When k is n, okay, we have to take k equal to plus n and k equal to minus n. And when k is n, you have this expansion like this. This will be 0, this a3, a1, that is 0, and we have to take only these terms. Okay, so we have this y equal to this. When you substitute for the coefficients, we the first term is a0 x to the power n, but we introduce n factorial here. Okay, so a0 n factorial over n factorial x to the power n, and here you have these terms when you substitute. Okay, and this can be written in general format like this. So y equal to this minus 1 to the power j a0 n factorial x to the power n plus 2j over 2 to the power 2j j factorial n plus j factorial. Okay, and we take this a0 2 to the power n, because here we have x here and 2 to the power 2j here, and we are writing x by 2 to the power n plus 2j. So 2 to the power n is introduced here to compensate for that. Here the power of 2 is only 2j. Okay, so we have y equal to a0. Okay, and this is written as y1. The first solution that we get, this is y1. That is a0 2 to the power n factorial. This is y1, the one solution when we put k equal to n plus n in the general equation. Okay, and the quantity, this quantity is the Bessel function. This is identified as the Bessel function. Okay, this term that we have already seen, this is the Bessel function Jn of x. And when we put k equal to minus n, the recurrence that relation that we are going to get is this. This here you will have minus 2n, and this is the recurrence relation that we are going to get. This is same as the previous recurrence relation. The only thing is here we have minus 2n. Okay. And the second solution, this is obtained by replacing n by minus n. So here for n we are taking minus n, and we have the second solution, and that is given by y equal to a0 2 raised to minus n factorial sigma j minus 1 to the power j x by 2 to the power minus n plus 2j j factorial, and this is what you get. This is y2 of x, the second solution. Okay. And if n is not an integer, then we have this is a distinct series. Okay, when n is not an integer, the solution that we get, that is a distinct series, and we have two solutions. What? Y1 for k equal to plus n, and y2 for k equal to minus n, and these two are distinct. Okay, these two are distinct. Now that is the case when n is not an integer. When n is an integer, trouble develops. Okay. For the second one, in this recurrence relation for k equal to minus n, when n is integer, what happens is for some value, we are actually taking a summation, so the value of j changes. For some value of j, the j plus 2 becomes equal to minus 2n. J plus 2 becomes equal to minus 2n, and we know what happens when j plus 2 becomes equal to minus 2n. This term will become 0, so this will blow up. I mean, that will be infinity or undefined. So the coefficient becomes undefined and the series will not exist. Okay. So when n is an integer and when j plus 2 becomes equal to 2n during the summation, when we are taking different values of j, or when j equal to 2n minus 2 or 2 into n minus 1, the series or the coefficient blows up. That means it becomes undefined infinity and we have no series solution. So this is the problem when n is an integer. So this catastrophe, this can be remedied by choosing a0 equal to 1 by 2 raised to n factorial. Okay, we are choosing a0 as equal to 1 by 2 raised to n factorial. So here this a0 is chosen as 1 by 2 raised to n factorial. So this will cancel. Okay, and what we will have is y1. This is equal to jn of x. Okay, and what about the second one here? This will go. Okay, because this is already gone. When we consider a0 as 2 raised to n factorial, this term is completely gone. We are left with this term only. For the second solution, we take n as equal to minus n, and we have the solution here. Okay, and the y2 for k equal to minus n now becomes this. Okay, sigma j0 to infinity minus 1 to the power j x by 2 to the power minus n plus 2j, and here we have minus n. Okay, now the problem is they are not independent. The two solutions are not independent, because we know for j minus n x, that is equal to minus 1 to the power n j n x. This we have already proved when n is an integer. So the second solution simply reproduces the first. Okay, they are not linearly independent. So we have failed to construct a second independent solution for Bessel equation by this technique. Okay, when the problem arises when n is an integer. If n is not an integer, there is no such problem. We have two independent solutions.